The binomial comes up in a lot of different applications, and there's one additional interesting thing that happens. So a binomial random variable has this mean n times p, and the standard deviation sigma is equal to the square root of n times p times 1 minus p. So one interesting result is if the sample size is large enough, we can approximate a binomial with a normal distribution. So to see what that looks like, we go into GeoGebra. Here were the numbers from that previous example. N was 12, P was 0.14. And this button up here allows you to put a normal curve on top of your binomial. And just to recall, you select binomial from the drop down here, enter N and P. So you can see that does not look very normally distributed. It's unimodal, but it's got a bigger tail on the right, so it's right skewed. But the interesting thing is if we increase N instead of 12, what if we go up to 50? And you can see that's looking a little better. We do have unimodal. It's definitely got tails on both sides. A little more symmetric, but it's still got a little bit more of a right skew, it looks like to me. But at some point, definitely by the time you get up to N is 100, that starts to look very, very close to a normal approximation. It's always going to be an approximation. It's never perfect, but you know, a lot of the time it's sort of good enough for what we need it for. But you can see how much the computer likes to slow down. If I try to enter 200, it enters 2, and then I have to sit and wait. It's because calculating binomial probabilities with very large values of n is very computationally intensive for a computer. These days, it's really not that bad a chore, even if you have to wait a second or two. But you know, back in the day, it was just nearly impossible without computers or in the very slow day of computers. So you can approximate it if the sample size is large enough, which means you have n times p greater than or equal to 10, n times 1 minus p is greater than or equal to 10. That kind of assures that the tails of your distribution aren't going to be pushing up against either the 0 or the 100% levels over there. Then the number of successes is approximately normal with this mean according to this formula and this standard deviation according to this formula. So for an example, in an old online Star Wars game, you wouldn't know if you had Force abilities until you were level 10. So you'd have to play the game for quite a long time before finding out if you could ever be a Jedi or a Sith or whatever. I don't remember if this is a real game or something I read about, but who cares? There are so many Star Wars games, we can just pretend it happened. But whether you could use the Force or not wasn't something you controlled. It was just determined randomly when you made a character. You would have to play the game for dozens of hours and hopefully get committed and enjoy your character before you found that out. But overall, let's say there was only an 8% chance that a player would be able to use the Force, so randomly determined when you started. So suppose 400 people joined the game. And so the question is, describe the distribution of the number of players who can use the Force. So if x equals number of players who can use the Force, then x follows a binomial random model with n equals 400, p equals 0.08. But x is approximately normal with mu equals 400 times 0.08, just that n times p formula from up here, and that's going to be equal to 32. And sigma equals the square root of 400 times 0.08 times 0.92 is 1 minus that. And I'll fill that in a second. So if you went into GeoGebra, you could enter this in the binomial. You could enter n equals 400, and then you have to sit and wait for a minute, depending on how fast your computer feels like being today. And then you enter p is, this is slow, 0.08. And then it'll generate the distribution. You can see it's kind of hard to tell because of the scaling, but it does look very, very close to a normal approximation. And then notice a nice thing for the binomial. GeoGebra actually gives us the mean up here. It's not displaying mu for some reason right now, but it should say mu equals 32, and then sigma is 5.4259. 5249. If that was the number, it doesn't matter. It was close to that. 4259. Okay. So what you could do is you could also, this normal curve that it's sort of drawn here in red, you could just go to the normal. You could enter n equals 32. The standard deviation is 5. I keep forgetting that number. 4259. Nope, missed the decimal. There we go. That's better. So this would give you the number of players in the game who could use the force, which is a random variable. It's pretty unlikely that like 50 of them would be out of those 400, but it's pretty unlikely that it'd be fewer than 20. So then you could go ahead and calculate probabilities of that, though. What's the probability that under 25 players, still out of that 400-person group, can use the force? So using the normal approximation, since I already have that up, we just do lower tail less than 25. And there's a bit of a discrepancy here because the normal distribution is continuous and the binomial is discrete, whole numbers only. So when it says under 25, what do? Do you do 24? It depends on the wording. I think WebWork is usually really precise about that. But if it said under 25, you could say 24. You could say 24 and a half. There's different rules on that. We don't need to get too picky in this class, though. But if you said under 25, that would be 24 or fewer. So we could say 7.02% or 24 or fewer. And then if we use the exact binomial to calculate the same thing, we go in here, we go binomial. And we have to wait for this to load again. Should have done this a minute ago. 400. 400. There we go, 0.08. Good. And then we do lower tail still at 24. Come on. And less than or equal to 24 lower tail give us 0.0793. So the exact binomial is 7.93% also for 24 or fewer. So the numbers are kind of close. They differ by less than 1%. It's not super accurate, but we're going to get a lot of use out of this when we talk about confidence intervals and such just very shortly over the next couple of modules.